playing around and building a beautiful proof for Viete's formula. Viete is also like known as Vieta. Yes, Vieta's formula like in polynomials is really famous, right? Yeah. Okay, and here's a like infinite product that basically gives 2 over pi, right? And it looks so beautiful because there are roots involved, right? Square roots of 2 involved that magically like give us pi, right? And that's so amazing, right? And in this video we are basically gonna see how we can like go around this infinite product and then build a proof for this. First of all, it's obvious. You might realize that this first term is just cos over pi by 4. Second term is just cos over pi by 8. This one is cos pi over 16. Actually, it's not obvious. I was joking. Okay, now how do you see the fact that these things, and in the next one will just be cos of pi over 32. How do you see this? Okay, first of all, let's go with that, and then after that we will see how we can basically find a proof based on this idea that these are all actually just cosines, right? So let's see. We know that the cos of pi by 4 is 1 by root 2, which is basically root 2 by root 2, right? Now how to get to next one? So we will basically try to use the half angle formula of cosine. We know that cos of 2 theta is equals to basically 1 plus cos 2 theta is 2 cos square theta, right? And that's why our cos square theta is just 1 plus cos 2 theta by 2, right? I can also say this as, let's say if I want to find half x by 2, then this is just 1 plus cos x by 2, right? Yeah. And now I can say that cos of x by 2 is actually square root of 1 plus cos x by 2, right? I'm going to modify this a little bit, and I'm going to write this as square root of 2 plus 2 cos x by 2. So we have found this formula that cos of x over 2 is actually square root of 2 plus 2 cos x by 2, right? Now, we know that like cos of pi by 2 is 0, right? From there, we can basically find cos of pi by 4. That will just be square root of 2 plus 2 into 0 by 2, which gives us root 2 by 2 as expected. Now we can also find cos pi by 8, right? And now we will see the benefit of writing it this way. We will see why. Now we know that again for cos pi by 8, we will basically use the fact that this is 2 plus 2 cos pi by 4 by 2, right? But here, notice that cos pi by 4 also has 2 in denominator, and there's also 2 over here, and they cancel out, right? So if I write it, it will just be 2 plus 2 times root 2 by 2 by 2, and this 2 cancels out, which gives us square root of 2 plus root 2 by 2, right? Now if you want to find cos of pi over 16, again you can go similarly. This will just be 2 plus 2 times cos pi by 8, which is again 2 plus root 2 by 2, right? And again these two cancel out, divide by 2. So this is just square root of 2 plus, now this is again just 2 plus root 2, right? So wait, I missed a square root over here. There's a slight problem. Wait, I did something wrong. Here, this is not actually just 2 plus root 2 by 2. This is actually square root of 2 plus root 2 by 2, right? And this is whole divided by 2. Again, these two cancel out, which gives us square root of 2 plus square root of 2 plus square root of 2 by 2, right? And you can see basically this 2 in the denominator just cancels out. If you want to find cos of pi over 32, and there's a 2 in front, because of which again we just get 2 plus this expression, which is 2 plus root 2 plus root 2, and everything divided by 2. So we see that basically there's this pattern in cos of like x by 2. If we first start with x equals to pi by 2, and all the following like cos of pi halves, right, for purpose for like, now we can, okay, so we can generalize this. Let's say for 32 there are 1 2 3 4 twos, right? Yeah, for 4 there's just 1, for 8 there's 2 twos. So let's say if you want to find cos of pi by 2 to the power n plus 1, then there will be such n twos, you see, n times, because for 4 twos this was 4 to the power 1, sorry, 2 to the power 4 plus 1. For 3 twos there was 2 to the power 3 plus 1. So you see the pattern, right? By 2. And yeah, so now we see how why these are actually cos pi by 4, cos pi by 8, cos pi by 16, and so on. So now that we know this, now we need to try to relate them, how we can actually relate cos pi by 4, cos pi by 8, cos pi by 16, and all this, right? Yeah, let's do that. Okay, we want to actually be able to evaluate this, right? Cos pi by 4, yeah, cos pi by 8, cos pi by 16, and so on. We want to evaluate this. So how do you think we should begin? Okay, now for this one, let us try to see a way by which we can get this expression. So and we can do that basically by breaking sign, right? Let's say if I have sine x, I can actually achieve 2 cos x by 2 sine x by 2, right? Using the half angle formula of sine, right? Let me make it a bit good line, straight line. Okay, again I can also break sine x by 2. That gives me now 2 square cos x by 2, and then cos x by 4 sine x by 4, right? I have again broken sine x by 2 into 2 sine x by 4 cos x by 4, right? Again I can break sine x by 4. That gives me 2 cube cos x by 2 cos x by 4. Again here cos x by 8 with sine x by 8, right? And I can go on, right? So right now I have 2 cube cos x by 2 cos x by 4, and I have, this is cos of x by 2 cube. Here's its sine of x by 2 cube, right? If I go up to like, if I repeat this n times, I will have 2 to the power n cos x over 2 cos of x over 4 cos of x over, this is, let's say, 2 cube cos of x over 2 to the power 4, and it will go on up to cos of x by 2 to the power n times, this is sine of x by 2 to the power n, right? Okay, now over here this is just going up to infinity, right? So over here also we want the n to go to infinity, right? So say on the limit n goes to infinity, let's see what happens in this case. In the limit n goes to infinity, the sine x will basically now be 2 to the power n. We know that this goes to infinity, but just wait and watch. Cos x over 2 cos x over 4, and then cos of x by 2 to the power n. Now n goes to infinity. Notice that x by 2 to the power n, this goes to 0, right? So the thing inside the sign goes to 0, and we know that at 0 sine of theta is just theta, right? So that's why it also becomes x by 2 to the power n, and 2 to the power actually cancels out. That's awesome. So you see that sine of x can actually be written as this product. So product from n is equals to 1 to infinity of cos of x by 2 to the power n, and also there's x in front. So you see we can write sine x as this product, x times product of cos of x by 2 to the power 2n, where n goes from 1 to infinity, and the product. So now if we have this, I think we can definitely evaluate this, because that's what we wanted earlier, right? Yeah, so we can evaluate that now. So let's say, okay, so over here, yeah, if we just substitute x as pi over 2, let's see what we get. We get sine of pi over 2 is equals to pi over 2 times product from n equals to 1 to infinity cos of pi over 2 to the power n plus 1, right? Because x is pi over 2. Now sine of pi over 2 is 1 and pi over 2 times this is just, now if you just open it, cos of pi over this will be 4, cos of pi over 8, cos of pi over 16, and so on, right? Now this goes to other side, and 2 over pi actually becomes the product that we wanted to evaluate, this product, right? Yeah. So we see that this is actually now cos pi. I can actually write in expanded form just to make sure that it looks beautiful, right? Cos of pi over 16 is root of 2 plus square root of 2 plus square root of 2 over 2, and so on. So we have proved the Viete's formula, or Viete's formula. Yeah. So the thing is, over here, like how beautifully the square root of 2 and pi is connected through trig identities, right? Basically, this trig identities just did a magic, Trig identities like could expand into infinite series. We could take a limit. We could cancel it out, and we could get an infinite product in terms of cosine for sine, and that gives us a formula. That's so amazing and awesome, guys. Okay, so in this way we have proved this formula for pi. There are also a lot of other formulas for pi, which I definitely recommend you guys to check out. And hope you enjoyed the video. Thanks for watching. If you liked it, do share with your friends as well, and I look forward to seeing you in the upcoming video too.